So hello and a very warm welcome to this, the third in a series of reflections on some topics in optical and radar polarimetry and how they interact. My name is Shane Cloud, and during my career I have been fortunate enough to work in both areas. But one key research topic that I was involved with was the application of polarization techniques to radar interferometry, now developed in radar imaging from space as polarimetric interferometric synthetic aperture radar, or just POLINSAR for short. A key enabler for the forthcoming ESA biomass satellite mission, and for more details about that, see my earlier YouTube talk on Faraday in space. In optics, of course, the classical double slit or DS experiment is still a major source of inspiration, exposing as it does the essence of the wave theory of light, and more exotically of the wave-particle duality of quantum mechanics. But optical waves also have polarization, as elegantly formulated by Henri Poincaré and his sphere, and here we use the double slit as a paradigm for linking together the subjects of polarimetry and interferometry. So, can differently polarized waves interfere? We shall see it is a good and subtle question that exposes some interesting concepts and provides a direct link to POLINSAR and the double slit. So here is the background to the talk, embodied in 3 recommended publications, one from radar on the original formulation of polarimetric interferometry, and 2 from optics, one dealing specifically with a full polarimetric analysis of the classical double-slit experiment, and the third a wide-ranging book covering the historical development of the double-slit experiment, as well as cataloguing the many ways in which it exposes the craziness of modern quantum theory. I acknowledge all of these in developing the ideas to come. Please take a look at the originals for more details. But here we concentrate mainly on providing something that is not in these individual publications, namely links between the radar and optical worlds. And to do this, we start with a review of the well-known double-slit experiment. So first described by Thomas Young, known as the last man who knew everything, first published this experiment in 1804 to secure the wave theory of light, although particle models lingered on into the 19th century, famously with David Brewster refusing ever to acknowledge the wave theory. So this simple experiment has been at the center of controversy, even from the very start. A wave hits 2 slits in a screen, generating 2 secondary sources that add on a screen to give peaks and troughs where the waves combine constructively or destructively. The mathematics is quite straightforward, just the addition of 2 complex numbers, with the phase of 1, phi, representing the different positions within the wave cycle. The intensity I is then just the magnitude squared of this complex sum, which varies in the y direction with a characteristic 1 plus cosine phi form, yielding the peaks and troughs of the pattern in the correct place, the distance between peaks being not a wavelength, but scaled by the geometry, particularly the ratio big D over small d, which is very much greater than 1. We will see this little equation appearing quite a lot in what's to come, the 1 plus cos phi. This simple form of the experiment works with any waves, water, light, or sound, but light is a transverse electromagnetic wave and so is polarized, having a specific direction of vibration in space, say horizontal h or vertical v. So it is natural to ask what happens if the polarization of the 2 slits is different. In particular, what happens if they are orthogonal, like horizontal and vertical? Do we still get interference? Well, let's go see. The short answer is no, but there is a more subtle answer that we will see. So here we have the same experiment, but now with polarizers across the slits, oriented to be orthogonal h and v, and then the interference disappears, or does it? Orthogonal waves can't interfere with each other is the usual conclusion made, but one we shall see that is not quite true and needs some qualification. There is a way we can make the fringes come back. To see this, we can again write down a simple mathematical description of the addition at each point from the 2 slits. Again, there will be 2 terms, one from each. But now we add not numbers, but vectors, 4-element vectors, k, called a Pauli vector. They have 4 complex elements, and they describe the way in which the polarization is selected at each slit in a very general form, not just 2 polarizers, as we have shown. So by changing K, the two slits can have any polarization response at all. Before proceeding to a vector description of the double slit experiment, let's pause to consider a bit more. What is this thing called a Pauli vector? Well, it's named for Wolfgang Pauli, who first used this set not of vectors, but of 4 2x2 matrices with ones and minus ones in them, called the Pauli spin matrices, defined from a simple algebraic requirement of squaring to the identity. He used them for a description of spin in quantum mechanics, but actually the algebra of these matrices makes them important also in polarimetry, where they are widely used to model physical structure in wave propagation and scattering problems. We will now use them to generate a vector from a matrix to describe the polarization behavior of each slit. So the set of 4 Pauli matrices forms a basis, a frame, which allows expansion of any arbitrary 2x2 complex matrix, big A, into a set of components, A subscript I. These form the elements of the Pauli vector. Two examples. The first one is a familiar one, the relationship between the 2x2 wave coherency matrix C and the Stokes vector G. The Stokes vector is just a Pauli vector representation of the matrix C. So we have this transformation from a matrix to a vector. But we can do the same with the 2x2 complex scattering matrix S, a general description for arbitrary changes in polarization in transmission or scattering by a slit or any other feature that we can consider. This then leads us to K, the Pauli vector for S, with elements formed as sums and differences of complex numbers as shown. And a key property of this vector K is its coherency matrix, formed as the averaged outer as opposed to inner product of K with its conjugate transpose. This makes a 4x4 Hermitian matrix T, which describes not just the vector K, but characterizes any fluctuations that may occur in the complexity of the wave scattering process. Hence, it is a measure of its coherence, and hence the name. Importantly for us, the 4x4 coherency matrix T, which has in general 16 independent elements, is in a one-to-one mapping with M, the more familiar Muller matrix, and so contains essentially the same information. We will explore this a bit later on. So, let's now return to the double slit experiment and ask, where did those fringes go when we changed polarization at the slits? So let's start with the easy case. Assume the slits have the same polarization, in this case V polarizes. So we first form the sum of the vectors, the second weighted again by the complex phase phi, accounting for differential propagation. Then we form the coherency matrix T instead of the intensity, and we see it has 4 terms. T1 and T2 are just the coherencies for the slits in isolation, but the omega matrices cause a mixing between K1 and K2. Here lies the interferometric information. By expanding for the example shown, we arrive at a single matrix, every element of which is multiplied by the fringe expression 1 plus cos phi. So we see fringes, of course. Now let's see what happens if we change one of the slits to be orthogonal. So now we generate orthogonal polarizations across the slits V for one and H for the other. So the inner product of 1 and 2, K1 conjugate transpose K2, now equals 0 because they are orthogonal states. Then we apply the same algebra. We get again a T matrix formed as the sum of slits in isolation, T1 plus T2, and still a mixing term, omega 1, 2. This mixing term still contains the fringe information, although the inner product of 1 and 2 is 0, the outer product that we need for T certainly isn't. And when we put it all together and add them up, we see that the matrix still has interferic information in it. We see the characteristic 1 plus cosine phi term appearing there in the first element. So why no fringes? What's happened to them? The answer lies in the Muller matrix. So let's see in a bit more detail how to transform T to M. Well, there are several ways to display the mapping from M to T. Here, we choose a single large 16 by 16 unitary matrix Q, since we will use this later on for a description of POLINSAR. The 4x4 matrices M and T are first themselves turned into vectors, this time by just stacking all the elements to form 16 element vectors small t and small m. These are now related to each other by this big but sparse unitary matrix Q. We see it has simple elements, just plus or minus 1, or plus or minus I, or just 0. Rather like a Fourier transform, in fact. It's easy to invert. You just take the conjugate transpose, making it easy to go back and forward between M and T as many times as we like. So now let's use this to convert our T for the orthopolarized slits into an M formulation. Just a quick reminder, the Muller matrix is a physically appealing formulation as it simply relates input to output Stokes vectors Gi and Gs for a system, for all possible states on the Poincaré sphere. For us, there are two key ideas. First, that the M11, the 1,1 element, is just the total intensity of the scattered wave. The second is, as we have seen, there is a one-to-one relationship between these 16 M elements and the elements of T. And also, in passing, a nice elegant form using an intermediate matrix Z was detailed in reference to, but here we will stick with T as it provides a direct link to radar. So, having calculated T, we can now use Q to form M for the orthopolarized slits, as shown. In fact, each element of the T sum also has a mapping to M, and so we can write the Muller matrix 2 as the sum of M1 and M2, that's the slits in isolation, and a mixing term, M12, which accounts for the interferometry. When we add them all up, this is what we get. Note that M11 is just equal to 1. There is no fringe information in the total intensity pattern. The interference pattern has apparently gone. But interference information lingers in other elements. We see phi. That means that by adding some polarization filters to the experiment, we can always recover fringes, even in the most general case. So, what is the most general filtering scheme? Here it is, in principle. Imagine some kind of polarization demon that sits by the slits and applies a weight vector, let's call it W, to the k vector that comes through. So W is a unit vector, and hence the reason for all the trigonometry you see in its makeup is just to make sure that it has unit amplitude. It all comes down to sine squared plus cos squared equals 1. The projection of W onto a k then makes a complex scalar, let's call them mu1 and mu2, and these scalar fields are then allowed to propagate to the screen and combine, just as in the original Young's experiment. And now we will see fringes, whatever k comes through the slit. So the question now is, do the fringes vary as we change W vectors, or are they always the same for all W? And this was one of the original motivations for POLINSAR. To start this process, let's look at how general weights can be incorporated into the double slit experiment itself. So here is how the filtering works in the general case. Again, we form the sum of mu1 and mu2 to generate S. The intensity is then generated I and involves again the two single slit matrices T1 and T2 together with the mixing terms omega 1, 2 and omega 2, 1. As an example, consider again the slits with orthogonal H and V transmissions. And let's choose a filtering W vector as shown, a projection in fact onto 45 degrees. For simplicity, let's make W1 equal to W2 as well. By doing the projection, we see the fringe function 1 plus cos phi appears. Our fringes are back. Okay, all well and good, you say, but how do we implement the polarization daemon to apply W1 and W2? There are several ways. In radar, we have the most flexibility, as we shall see, but you can do it in the optical double slit experiment as follows. So here is one way to make a polarimetric interferometer. Assume again we have orthogonal slit polarizations. Now imagine we can control the polarization of the source. We can polarize it in any way, any state on the Poincaré sphere as shown, represented by a Stokes vector, GT. Equally, we can put a polarizing filter, if we wish, in front of the detector, Again, we are free to choose any state on the Poincaré sphere with Stokes vector GR. The whole system now has a single W equivalent form, just like a daemon projecting W vectors after the slits. To see this, first consider the way that I, the intensity variation on the screen, varies for W and Stokes vectors. So we have two forms, one involving T, projection with W, and one involving M with GR and GT. And now they must be equal. So by vectorizing M and T, we then obtain a new algebraic form of this as just a vector P projected onto T. Remember the vectorized form of the coherency matrix. Now, the advantage of this is that we can find W for a given GR and GT. It is, in fact, the maximum eigenvector of a matrix constructed from P. Just cut the long chain of elements in P into rows, as shown, 4 rows by 4, to make mat 4. Then find the eigenvalues of mat 4, and for any Stokes pair GR and GT, we can then find W as the eigenvector. And so, of course, W1 equals W2 implicitly in this. Now, this may seem like a general method, but of course, we know W1 and W2 need not be equal all the time, and there are surely other ways to filter, and that is what POLINSAR is all about. So to see how filtering is much more general than just effectively choosing Stokes vectors of source and detector, let's look at some examples. Firstly, if the Stokes vector of source and detector are equal, then it follows that W will always be real. Clearly already not using full capacity, as W can be full of complex numbers, not just reals. So how to access these extra degrees of freedom? Well, if we make GR and GT different now, then it does follow that W will be complex, but still not the general case. In other words, we cannot always go from a general complex W back to a Stokes pair, and there is a simple test to show this. The condition that we can go from a complex W to a Stokes pair has got to do with the eigenvalue spectrum of the matrix mat4 that we met earlier on. Only if it is rank 1 can we make the mapping. But clearly, in general, mat4 can have a full spectrum, and so there are infinitely more possibilities than just Stokes filtering. Here is a simple example. W with a 1 in the first position only. This has an eigenvalue spectrum of all 1s and has no mapping to Stokes pairs. And we have not yet even talked about the possibility that W1 and W2 can be different. So how do we access all these degrees of freedom, all these different possible ways of filtering? So, to answer that, we have to think a little differently about how to generate the W filtering. And that is what POLINSAR is about. And the reason this is important is because of partially polarized waves, which we now consider. So what happens if we get partial polarization in the double slit experiment? Well, this can arise from complexity, which leads to depolarization. That is, the signals from the two sources may be dynamic, spatially or temporally, and this leads with averaging to loss of coherence in the interferogram formation. We will see that it is in such scenarios that the full W1, W2 flexibility comes into its own. At the heart of such issues is the fact that sometimes interferograms are formed with such partially polarized waves. The distance from peak to trough of the interferogram of the fringes reduces. Fringe visibility is degraded. So how is this reflected in the formulation so far presented? Well, spot the brackets around T. This means some kind of average. And by using Q, it translates into an average of M. And now our interest centers on the average of these mixture terms, T12 and M12, the mixture terms that carry the interferometry information. And the average over phi makes these things sometimes quite small. In the extreme, if we have enough fluctuations, then the phase term averages to 0, and both T and M are just the sum of those of the individual slits. Interferometry then truly has disappeared. It's not just hidden in a matrix. In reality, we can encounter the full spectrum of problems, of course, from full coherence, like the ideal double-slit experiment, through arbitrary loss of coherence due to complexity and diversity, all the way to the worst-case scenario where we get independent slits. It is fair, therefore, to ask, can we choose the pair of weights W1 and W2 to maximize the coherence for any problem, and hence extract the best quality interferogram, the one with the best fringe visibility? This was one of the main motivations for POLINSAR. So how to get the best quality fringes for any given problem? Well, to see the answer, we first construct a double length Pauli vector. Q has 8 elements, 4 for each slit. And now we form the coherency matrix of this bigger vector to itself, an 8 by 8 Hermitian matrix, which, as we can see, can be further partitioned into components we have seen before. The two isolated slit matrices T1 and T2, each of them 4 by 4, sit along the block diagonal, and the interferometry parts, omega 1, 2, on the off diagonal. This approach also scales to an arbitrary number of slits. For n slits, we obtain a 4n by 4n matrix. Now, for each pair of slits, called a baseline in radar interferometry, we can then project the data onto two weight vectors W1 and W2 to form a 2 by 2 projected coherence matrix, J, as shown. The coherence or fringe quality can then be just defined as gamma, the coherence we get from this matrix J. Here again we see the familiar component matrices appearing in numerator and denominator. The problem now is to choose W1 and W2 to maximize gamma. Note that in radar terms, it is straightforward to apply the weights. Imaging radar measures directly the Pauli vectors for each slit, and so we can just project them in the data processing. If you want to know how radars do this, see my earlier YouTube presentation on Poincaré's radar. This problem can be solved analytically using the method of Lagrange multipliers. So the details of the optimization can be found in reference 1, and here we just showed the main result. So to find the maximum coherence, the best fringe visibility, you should use W1 and W2, found as E1 and E2, the maximum eigenvectors of two matrices formed as products of the three component matrices introduced earlier. And the resulting maximum eigenvalue of these compound matrices is the square of the maximum coherence. So since this original publication, there are now several variations of this optimization scheme developed in the radar literature, but they all have in common this idea of using weight vectors to enhance the interferogram, just as we applied to the double slit experiment. Fringes never completely disappear until all coherences fall to zero. That's the mantra from radar interferometry. It is all a matter of using the right filters. So we conclude by highlighting some of the connections between optical interferometry of the double slit experiment and radar interferometry. In this talk, we have extended both to include variations in polarization of the waves through the slits in optics or from ends of a baseline in radar. A key link is through the coherency T and Muller matrices M, which in a sense are equivalent. In both cases, we have an expression for the sum of signals as the response of each slit alone, with a mixing term M12 or T omega 1, 2, 2, 1. This contains the interferometric information mixed with polarimetry. In the classic double slit experiment, when orthogonal polarizations illuminate the slits, then interference disappears, but we showed that it's still there. It's mixed in the elements of M and T. It only really goes away when the coherence goes to zero. And this leads us to the idea of a polarization demon, filtering by weighted projection to expose the fringes again, even when orthopolarizations are used at the slits themselves, as we have shown. We examined one way in which these weights could be generated by controlling the Stokes vector of source and detector, but also show that this does not exhaust possibilities. You can't just think that this is equivalent to Stokes filtering. The set of weight possibilities is much larger, a richer mathematical landscape to explore, and one well suited to the technology of radar imaging. And I would encourage you to look in the radar literature to see the various ways in which people have explored this landscape. We then showed how to use this flexibility to maximize fringe visibility in the case that the waves are partially polarized. In this case, we use the same component T matrices found for the DS experiment and use them in a composite 8x8 matrix. This leads directly to a technique for finding W1 and W2 that maximize coherence. Thanks for listening.